We're going to look now at constant acceleration with vectors. So these are the same vector equations that we have seen before. These are the same equations we've seen before except with vectors. So instead of v equals u plus at, it's vector v equals vector u plus vector a times t. Likewise, for the displacement, you've got the vector u and the vector a involved. Notice your t, which stands for time. Time is not a vector, time is just a scalar. And also we have got this one here. I'll add in one more, and it is this one. So your displacement is equal to vt minus a half a t squared. Okay, so there's a wee bonus one for you as well. Not used as much, but it can be useful. Okay, this example says, during a 20-second period, the velocity of a boat changes from 8I plus 12j meters per second to 6I minus 5j meters per second. Assuming the acceleration of the boat is constant, find the acceleration of the boat. So let's just set it up as we would have done before. So my time was 20 seconds. My u, I'm going to write this as a column vector, was 8, 12. My v as a column vector is 6 minus 5. And a is what we're trying to find. So we're going to, in this one, we're going to then say, just write down vector v is equal to vector u plus vector a times t, and then we'll just fill it in. So that's 6 minus 5, that's my vector v. My vector u is 8, 12, and then that's going to be plus my a times my t, which is 20. I'm just going to write that as 20a. It'll be a nicer way to write it, so it's 20a. Now bring the 8, 12 across, and it subtracts 6 minus 8 is minus 2. Minus 5 minus 12 is minus 17. And that equals 20a. So your a is just going to be equal to 1 over 20 upon minus 2 minus 17. And I would probably just write that as a regular vector because I had given it in that form. So that's 1 over 20 times minus 2i minus 17j, and that's meters per second squared. Okay, the next bit says find the distance traveled during this 20-second period. So I'm going to use, for this one, I'm going to find my displacement first. So displacement is a half u plus v t. So I've got all of those things already here, so I can just get started this one. My Sn is equal to a half, and my u plus v, that's going to be 8, 12 plus 6 minus 5, and then that's times my time, which was 20. Sorry, let me just zoom in on this wee bit. So that was my half u plus v upon t. So if we just do half times 20, that just gives you 10. That just gives you 10. And then if you do your 8 plus your 12, that gives you 14. And 12 minus a 5 gives you 7. And then if you just multiply in by that, you'll get 140 and 70. Now that is my displacement. To find the distance, your distance is going to be equal to 140 squared plus 70 squared and the square root. And whatever that is, let me just work that out on my calculator here. 140 squared plus 70 squared, square root, and I got 70 root 5. Perfect answer of 70 root 5. And let's just give the two sig figs, 156.52, and that's going to be meters to two decimal places, sorry, I've gone to, and that's it. This example says a particle A has an initial position vector of minus 5 minus 1 meters, initial velocity of 2 minus 1 meters per second, and a constant acceleration of 2 meters per second squared. Particle B moves with constant velocity of 10 meters per second. Find the time at which the two particles are moving parallel. Okay, so moving parallel means that their velocities are going to be the same. So particle B moves with a velocity of 10, 10. So any vector parallel to that would be AA. So it could be 5, 5, it could be 1, 1, it could be 6, 6, but it's going to be the top thing is going to be the same as the bottom thing. So that's really what we want to do. So for your, that's for particle B. For particle A, the initial velocity was 2 minus 1. The acceleration was 1, 2. And we want to find the time at which it is equal to, it's going parallel to this. So we want to say our velocity, final velocity then, is AA. And we want to find basically the time. So we just can put AA, that's my V, sorry, I'll write that in, apologies. I should have said V is equal to U plus AT. And then we're going to fill this in. So filling this in then, we would have A is equal to my U, which is 2 minus 1, and then times my T times my A, so T times 1, 2. So we have to find the time at which this is the case. So here, I would just say then that means for your I's, then A is equal to 2 plus T, and for your J's, A is equal to minus 1 plus 2T. So we've got A is equal to this, and A is equal to this, so let's just put them equal. So 2 plus T is equal to minus 1 plus 2T. Bring all the T's to the right-hand side, you'll have 2T minus T, so just T. Move all the numbers to the left-hand side, you'll have 2 plus 1, so 3. So your answer for the first part, for your part A, the answer T is equal to 3 seconds. So at 3 seconds, they're moving parallel to each other. Just go through that first wee bit again. Your second point B moved with a velocity of 10, 10. That meant as you go across 10, you go up 10. So if you're going parallel, anything parallel to that would be the same. Would be like 1, 1, 2, 2, or in the general AA. So that's where that came from. So that's all we were doing there. Okay, right, part B says a third particle C has an initial position vector of minus 1, 7 and an initial velocity of 2, minus 4 and a constant acceleration of minus 1, 1. It collides with A at time t. Find the value of t. Okay, right, we're going to look at A, and I'm going to use my R for my position vector in this one. So we're going to look at this as my particle A, and R, my final position vector, is my initial position vector plus, and it's moving at a constant velocity, so it's going to be its initial, it's moving a constant acceleration, its initial velocity times time plus a half my acceleration times time squared. So this is your initial displacement plus what you have moved in that time. So we're going to fill that in. So for R, let's say R subscript A is equal to the initial position vector of A was minus 5, 1. It moves with a initial velocity. I'm going to say that's t times n 2 minus 1. And then that's going to be a half times my A, which is 1, 2, times my t squared. And then we'll do the same for, I think it's particle C, yep. So particle C, so I'm looking at this bit here. I've done in this lovely blue colour. So that's the bit we're looking at here. So it says a third particle C has an initial position vector. So again, for C, and again, I'll just write that down. This is your R0 plus U times T plus a half AT squared. And remember, all these things are different for the C. So for RC then, its initial position vector is minus 1, 7. Its initial velocity, so T times the initial velocity is 2 minus 4, and a half times your acceleration, which is minus 1, 1, times your T squared. Now you've probably guessed what we're going to do. We're going to put RA equal to RC. So put position vector of A equal to position vector of C, because if they collide, their position vectors must be the same. So it's a wee bit of work to do, fair bit of work to do this. So you've got minus 5, 1 plus T times 2 minus 1 plus a half times 1, 2, and that's times T squared is equal to minus 1, 7 plus T t times 2 minus 4 plus a half times minus 1 times t squared. Now find the value of t, so they meet at a time t. So we just need to look at one of these. Now I'll check just for the purpose of this video, just to see if I'm right. I'll check with my j's, but I'm going to just do the i's. So for the i's, minus 5 plus 2t plus a half times 1 times t squared, so that's going to be 0.5 t squared is equal to minus 1 plus 2t, and then that's going to be minus a half times t squared. Let's bring everything to one side. All the t squares to one side, everything to one side. To the left hand side, you'll have t squared. Oh, we'll have t squared minus 4 is equal to 0. Okay, very good. T squared minus 4 equals 0. That means t squared is equal to positive 4. That means t is equal to plus or minus 2. So your answer, t is equal to 2 seconds. Okay.